Okay, so this is a webinar on the fundamentals of Lagoon aeration. I imagine if you're coming into this webinar, you have somewhat of an understanding of Lagoon aeration. So this is meant to be not really an Aeration 101 kind of webinar. Maybe this is a 200 level course where we get into some of the hairy details, but not those that require a graphing calculator to get just right. So what you see in the background here is an aeration basin at an industrial plant that treats wastewater sugar beet waste, and it is a very, very heavily aerated cell. About half of the work that we do is industrial and pretty intense like this, and about the other half of the work from an aeration standpoint is municipal, which tends to see a lot less aeration. But I really enjoy this photo because you see a lot of aeration out there, a lot of activity. We have a dissolved oxygen meter hanging out right here, and you can see that the bacteria is responding pretty well because it's creating foam. This basin had just started up, and when you see foam, it's an indicator of bacterial, especially young bacterial activity. So what you're seeing is a young biomass starting right here, which I think is pretty neat. So before we get in, I need to share something here that happened. Slide is not changing over. There we go. Need to share something that happened last night. I was actually doing some aeration design work on the west side of Iowa, and I will say that this has nothing to do with aeration specifically, but it's so wild that I had to share it. I was flying back home to give my webinar the next day, and the plane that I was in, which was the second plane they brought in because the first one failed for mechanical issues, ended up hitting the jet bridge, which you can see right here. So I can tell you that the pilot was not very happy about this, but I really appreciate the call sign of the airport in the background. I think this picture or this video kind of provides the commentary for the whole situation. So I am not at my desk, had to rework the presentation a little bit to make that work. I am in the finest one-star hotel that American Airlines did not want to pay for, but I do have Wi-Fi, which is great. And hopefully you don't hear my neighbor flushing the toilet in the background, but we can power through. So from an outline standpoint, what are we going to be doing here? I'll start with a brief introduction of myself. I can do that now, but then an introduction of where I come from, so you can understand why we are credible to provide a webinar on aeration. We will then do a review of aeration itself. What is it? Why is it important? And how do we accomplish this aeration? We're not going to go too far in depth on this. It's more of a recap to refresh your memory. Next, we'll look at the 8 critical components of aeration design, things that you should really focus on when you're developing a basis of design or plan to add aeration to your basin. Then we're going to look at mixing, and you'll learn a little bit more about this moving forward, but mixing is what I consider to be the real most valuable player of aeration, and you'll learn why a little bit later. And lastly, we have some quick hitter aeration considerations, things you should keep in focus when you're considering adding aeration or modifying aeration at your site. And then just over on the right is a photo of me in that same basin I showed you at the beginning. As you can see, there's a lot more young bacteria activity. This is a few days later as the bacteria are growing and respirating with the oxygen that is being imparted. I can tell you this was a very, very smelly basin, and those bubbles were a lot of H2S as well. So that was not a fun lagoon to row across, but that's me. I've been in and out of lagoons. I've deragged surface aerators. I have swam around aerators, not in a lagoon, thank God. And I will say, there's this conventional wisdom that you can't swim around an aerated cell. That is not true, but you cannot swim in a complete mixed cell. So there is a difference. Lagoons are not as dangerous. And moving on. So my company here, Triplepoint, we have this belief that lagoons do it better. And if you've been around the Triplepoint ecosystem, you've heard this a number of times. And what we see here is that lagoons are the best type of treatment system for small communities. Typically, the infrastructure is already there. It's a very reliable, consistent method of treating wastewater. At the same time, we do believe that lagoons can do it better. And as these operators and engineers of these plants are being told that you have to hit phosphorus, or you have to hit nitrogen limits, the conventional wisdom is you've got to go to an activated sludge plant. And as the lagoons do it better people that we are, we say, no, you don't have to. Lagoon simply wasn't designed to treat phosphorus, or it wasn't designed to treat nitrate, but it can do it. We just need to modify it to do so. So lagoons can do it better to the point where we can modify lagoons to give you an effluent as good or better than the activated sludge plant. But it does require a bit of a tailored approach. There is no one-size-fits-all solution to lagoons. Every lagoon's different. Some are fat, some are deep, some are wide. Some have high flow, some have low flow. Same with loading. So the solution to each individual plant tends to be different from the plant that we do prior to that. So it does require a tailored process. And from a triple point standpoint, we do back up everything we design with a we say it, we do a guarantee. And as a part of that tailored process, it does require, it's an iterative approach. So usually the first design that is developed on a wastewater lagoon is not the design that we eventually end up with. So I think you'll learn some tools in this presentation here to kind of help you go through this iterative process when you're doing your designs. What do I need to pay attention to? What do I need to tweak? And what might I want to optimize to get the absolute best aeration design moving forward? But first, we have to talk. And I know this is really controversial in the aeration space, but I wasn't going to do this, but I have to get it off my chest. There's a difference between aeration and aeration, and I feel like there's this divide. Half the people call it aeration, half the people call it aeration, and aeration is like a virus. Like once one person starts to say it, the next person starts to think, well, wait, maybe I'm saying it wrong, and that spreads and it spreads, and sometimes I catch myself trying to say it. So I'm just here to say I'm putting my flag in the ground. I am team aeration, and that's what I'm going to call it through the rest of the presentation here. So what is aeration? The US EPA has a different definition than what I think most people think of when they think of aeration. They think aeration, oh, well, that's putting oxygen in the water, right? Simple, just blowing air out there in one way or another. And that's true to an extent, but the EPA goes beyond that and says aeration is not just adding oxygen to the water, but also adding mixing such that the oxygen and the waste and the bacteria that's already in the water are in constant contact. I could put all the oxygen in the world in one corner of your lagoon, but if it doesn't reach the other corner of your lagoon, we're not actually aerating your entire basin. And the next, from an aeration recap standpoint, why do we want to aerate? Why is this important? And we like to think of aeration as kind of the heart of your lagoon treatment. And you could be out there saying, well, I don't have any aeration. What are you talking about, Brady? You do, actually. You're relying on aeration whether or not you're aware. It's happening in your lagoon, even if you're not adding it to it. It's just a matter of degree. And we'll talk about how your pond's already being aerated, even if you have no equipment. But what we find is the more aeration you add, the more treatment you get. And that applies from a BOD standpoint, from an ammonia standpoint. In some cases, your lagoon may not be designed to handle the BOD or ammonia loading it's getting, or maybe it is designed, but you'll find later in the presentation that the more aeration we add, we can actually increase the treatment capacity in your existing lagoon. So if you're a small community and you've got a lagoon that's chugging along just great, but you have, I don't know, a dairy that wants to move in next door and provide a lot more waste. This is great. It's more jobs for your towns, more money for the wastewater treatment plant, but you've got to use the infrastructure or the footprint you have. Adding more aeration will increase that. And we'll talk about that. Aeration really does eliminate odors as well. You'll know an under aerated lagoon as soon as you walk by, or sometimes as far as a mile away, it smells like rotten eggs or H2S, has a very smelly odor to it. If you go to a properly aerated pond, it smells just like any other pond that you might let your kids fish in. It's got this just neutral kind of musty odor that water bodies have. So a well aerated pond does eliminate odors. It also mitigates algae growth. The more aeration you have, the more mixing you have, and algae does not like to be in a well-mixed environment. It will minimize sludge accumulation. It helps prevent short-circuiting, and short-circuiting is when you have the waste coming in your influent pipe and it kind of just beelines it for the effluent pipe. The more you churn up that water and the more you mix it up, which comes with aeration, the more you're going to hang on to those solids in the system and digest them for a longer period of time. With aeration, you can lower your operational costs. So if you have an old aeration system that was broken or maybe was designed in the 1970s and is not very efficient, putting more efficient aeration in your system can actually take and lower your aeration or your energy spend by up to maybe 50%. So it's pretty powerful. And overall, aeration is the key source for predictable, reliable, consistent performance. Across the board, if you have aeration in your lagoon system, it'll account for about 80% of the money your town's spending to treat wastewater. That's just where most of the energy goes. And most of the energy goes there because that's what's doing most of the heavy lifting. So we're here to talk about, what are the key components here and how do we optimize it? Oh, and I have a video. So this is more of a complete mixed cell. This is an industrial plant as well. They have some surface aerators in the background in cell 3. Cell 2 here is some diffused aeration with surface laterals and some onshore blowers. So how we know what aeration is. We know why it's important in my lagoon system. So how do we get it out there? Again, this is a bit of a recap for a lot of you here. The first important one is air-water interface. Aeration is primarily done with ambient air. The air around us, the air that we're breathing, is around 21–22% by concentration of oxygen. It's primarily nitrogen, which is largely inert. We don't transfer that to the water. But we want to take the oxygen that's in the air and get it into the water. And that's done with an air-water interface. And we can do that by moving the water to smash it around with the air, or we can move the air to get it in the water. You'll hear about that in a minute. Pressure is also important. When there's a larger pressure differential or there's more pressure to the air, we can get more of that oxygen. It essentially pushes the oxygen from the ambient air through the air-water interface and to the dissolved oxygen state inside of the water. Turbulence is very important as well. Turbulence in that interface encourages the transfer of oxygen across the barrier. And circulation is important too. So turbulence is more of like a Reynolds number, kind of micro level mixing. Circulation is more of a macro mixing. So if you take a look at the photo over here on the right, this is a design, this is intended to be this way, complete mix in this area and no mixing over here. But if we're expecting to get the air that we're putting in right here all the way down to this corner of the lagoon, we're not going to. So in order to aerate, we need proper circulation and build that into our design to make sure we're getting air everywhere we want it to be. And the types of aeration we're going to discuss are natural aeration, and this is for those people that don't have any equipment out there but are relying on aeration. We'll look at mechanical agitation, air diffusion, and oxygen injection. The first one is natural aeration. So here's a pond. As you can see, there's nothing out there. There's no bubbles. There's no motors at the surface of the water. There's no windmills. There's no nothing. This pond is heavily aerated. You might get out there and find a DO of 6, 8, sometimes 10, 12, 20 in the summertime. And that's because there is air in that pond. So it's facultative, meaning the regulators and the engineers expect that there are some areas of this pond where there's no oxygen and there's anaerobic digestion, but we're also capitalizing on free aeration. And this comes from the large surface area. Facultative ponds tend to be pretty shallow, but have a large surface area. And this is where we create the air-water interface. And oxygen is actually transferring all across the surface. And as the wind blows across it and the water ripples and folds over, we actually add more oxygen in that process. Next, there's also algal respiration. So algae, all day long, as they photosynthesize, they take in the energy of the sun, they take in carbon dioxide, and they release oxygen. And this is how they fix carbon during their life cycle. And when they release oxygen, they actually do so in a way that can even supersaturate the water above the saturation point of dissolved oxygen of that water. So this is why you might get out there in the middle of summer and see DOs as high as 20, which is well above the saturation point in warm weather. As you can see in this pond, there's plenty of algae. It's the green stuff. It is kind of a double-edged sword though, because when those algae stop receiving sunlight, they switch their type of respiration and they actually start consuming oxygen again. So at nighttime, they're sucking the oxygen out of the water. Daytime, they're aerating your pond. And lastly, you might have a waterfall in your effluent or in other parts of your wastewater treatment process. When you get that turbulence and water's being churned up, oxygen will be transferred in those applications. Next, we have surface aerators. This is surface agitation. Surface aerators throw the water up in the air or move the water to either expose the water to the air or to push the air down through the water. So you might see splashers like this. This is a brush aerator here. This is an aspirator which sucks the air down through a propeller at the bottom, jet aerators. But the idea is we're moving water to get air into it. These are relatively inexpensive from a technology standpoint. They're pretty easy to get out there on their pond. I've heard them described as like frisbees, just kind of throw them out there. But from a downside standpoint, you do tend to have a lot of motors that are out exposed to the elements. And this is not necessarily the most efficient treatment technology out there if energy efficiency is of importance to you. So we'll look at that graph-wise later. But this is one of the more common treatment technologies. You see it out there quite a bit. It's very well tested, very well tried for the past 30 years, and it is a common aeration methodology. The next methodology, this tends to have been blossoming a bit more in the past 20, 30 years, is air diffusion. Instead of throwing the water up into the air, we're going to pump the air down into the water and release it. And yet the principle behind this, the idea is pumping air is simply less energy intensive than pumping or moving water. So this tends to be lower from an energy cost standpoint. And you can see here, here's a side profile where the bubbles are released at the bottom and the bubbles just rise to the surface. And the concept is, as they're rising, the oxygen is being transferred from the surface area of the bubble. Air diffusion is mostly moving in lagoon space towards finer bubbles, and the finer the bubble means it has collectively the millions of bubbles that you have out there have a higher surface area to transfer that oxygen, because again, it's really all about surface area. If you compare these small bubbles to the coarser bubbles at the bottom, these bubbles have a larger volume and a smaller surface area per that volume, so they're not going to transfer as much oxygen to the water. The benefit of coarse bubble, though, on the other side, is that they do mix very well. They rise turbulently, so there is a little bit of a boon to their aeration from that perspective. Fine bubble aeration is going to be about half of the energy cost of surface aeration, the power cost, and then coarse bubble aeration is going to come in about 20% higher, 30% higher than those fine bubble numbers. So coarse bubble tends to come right in between. Fine bubble diffusers do require maintenance, though. And coarse bubble, as you can see, it's just essentially a pipe with holes in it. So it doesn't really require any maintenance over the course of its lifetime. So we will talk about maintenance a little bit later. And then here's just a bottom down view of, if you strip away the water, what do the diffused aerators look like? They're put usually at the bottom side of the wastewater lagoon system, and the bubbles flow up from there. So this is kind of a cutaway view. And then lastly, the last aeration option or category that we're talking about here is oxygen injection or air injection. Oxygen injection is not something we see very often. I did last year go to an industrial plant who was pumping in around $1 million a year of pure oxygen into their lagoon, and I was just thinking to myself, like, you do realize there's free oxygen in the air all around us. All you gotta do is pump it in. So I thought that was not the best way to do things, but there are a couple of outfits right now that are doing air injection, where they take the ambient air, they either super concentrate the oxygen in it or just pump the air in such a fine way that the air just clouds in. It barely even rises, in some cases doesn't rise. So you get this kind of cloud effect. And I think this is kind of a neat technology and something that we've explored off and on for the past 5 years, is in conjunction with what we do. The biggest challenge that I've had into integrating it into our designs currently is the mixing component, where this is designed to not rise. It's designed to not cause turbulence. So it does provide oxygen to the water, but the question is it going to be providing the mixing such that this oxygen is spread throughout the basin? So from my perspective, this is a great aeration device to use in conjunction with other aeration and mixing devices, as long as you have mixing. But it does not complete the US EPA definition of aeration, in that it doesn't provide the air and the mixing to spread it throughout the basin. So what are the critical factors of lagoon aeration design? These factors are a little bit academic to an extent, but they're also really tricky. We do phosphorus removal, we do nitrogen removal, denitrification, and those sound trickier, but really the trickiest thing we do is aeration, or at least the most nuanced. There's a lot of factors, there's a lot of detail, and oftentimes when you change one factor, it might change 13 other factors. So it does take a kind of a critical eye to make sure that this is being done properly. And the ones that we're going to focus on today are kind of fall into two categories. On the left side of the screen, we have aeration demand. This is often known as actual air or oxygen required, or AOR, and we'll call this demand. This is what your lagoon wants. This is the actual oxygen your lagoon requires for bacterial digestion. And we'll talk about where that comes from. We'll talk about the oxygen loading rate, how much air we put in per that demand, and mixing as well. And then on the other side of the, scale you have here, aeration delivery or supply. So if our lagoon wants A, we want to give it A, we don't want to give it B. So the aeration delivery is through a term called FTE, or field transfer efficiency. And this is a combination of oxygen transfer efficiency of your equipment, standard aeration efficiency, and the alpha factor, beta factor, theta factor, and residual dissolved oxygen requirements of your lagoon. And we will talk about each, or the high points of those. But the important thing here is we need to match your demand with supply. If your lagoon has a water volume, it's got bacteria, it's got loading, and those bacteria want to breathe. We're not making them treat anything. We're just providing them the oxygen such that they can treat the wastewater. If we don't provide enough to meet their demand, they might go anoxic, they might go dormant, they might not work, you might get odors in your lagoon. So meeting that demand is pretty important, but you don't want to supply more, you don't necessarily want to supply more than those bacteria require, because if you do, you're just burning up cash to do nothing at a certain point. Unless you're trying to increase mixing, putting more air will raise the DO, but not do a whole lot for your system. So it's kind of a delicate balance you want to chase here. So the first one is air demand. And the key one here is AOR. This is what we chase in most of our designs. What is the oxygen required for your lagoon? And the biggest impact or contributors to this is BOD, but BOD5 is not necessarily comprehensive. BOD5 is actually, you have carbonaceous biological oxygen demand, and you have nitrogen biological oxygen demand, and they have different levels of air demand. So if you look over here, the carbon component of your loading, CBOD, requires 1.5 pounds of oxygen for every pound of BOD that we put in. And this is for every single day. Some states require you to put in as much as 2, but that's not really necessary. From a ammonia standpoint, or sometimes people will use a TKN number, the nitrogen requires 4.6 pounds of oxygen for every pound of ammonia or nitrogen that you're putting into your lagoon that you want to convert. But I think the important thing here also to discuss is the fact that BOD5 is not the entire picture. So for those of you that may not have heard the story, BOD5 is simply a measure of what happened was basically London, which was one of the earlier civilized, modern civilization countries in the world, realized they're putting too much waste into the Thames River and it stinks and the fish are dying and we don't like that. So they studied it and they figured out there's an oxygen demand of the waste you're putting in. And BOD5 comes from the fact that the Thames River flows for about 5 days from London to the ocean, and they didn't care about it after that. It goes out in the ocean, becomes fish river, but they didn't care what the oxygen demand was at that point. But there still is an oxygen demand beyond BOD5. Yeah, BOD5 is not the entire picture, and things continue to break down. And some things break down for a really long time, and we got to provide the air for that. That's what I was talking about. And I simply wanted to reference as well the fact that it's kind of like, we're creating a lot of things these days that don't break down at all. This is a cheeseburger that's been sitting out from McDonald's since 1999 and it hasn't broken down an ounce. So some things take a really, really long time to break down. I think maybe the cheeseburger's a BOD of around 8,000, but just something to consider is that air needs to be required to break down things that are hanging out your lagoon longer than 5 days. So from an AOR standpoint, let's take an example. Let's say you have a lagoon, 200,000 gallons per day with 250 milligrams a liter of CBOD and 30 milligrams a liter of NH3N or ammonia. So this would produce an AOR of about 855 pounds per day. And as you can see, it's 50 pounds of ammonia times 4.6, because that's the loading rate for ammonia, and 417 pounds of BOD times 1.5, which is the loading rate for BOD, for a net of 855 pounds of oxygen per day. That's the demand that this lagoon wants, and we have to find a way to deliver that. So from an aeration supply side, what do? How do we get it out there? The first component of this comes down to the oxygen transfer efficiency of the particular equipment that you're using. Oxygen transfer efficiency is a marker more for diffused aeration, and we'll talk about another marker that is more used for surface aeration and compare the two. But from a diffused aeration standpoint, we have oxygen transfer efficiency. And this is a measure of how fast or how well we can transfer oxygen to clean water with a particular device. And in general, this is measured in % per foot of submergence. As I mentioned earlier, oxygen transfer efficiency is all about bubble rise time. The longer we can rise in the water column, the more time there is to transfer that oxygen. So the deeper we are, the more feet we have, the higher the overall oxygen transfer rate. So if we have a piece of equipment that's 2.1% per foot of submergence at, we'll say a 12-foot water depth, so the air release depth will be around 11.25 feet. The standard oxygen transfer efficiency for that equipment in that basin would be about 23.5%. An important thing to note with diffused aeration is that the first 18 inches is actually the most efficient. So if the air is released right here, for the first 18 inches, it's the most efficient. And that's because down low, the bubble has the most oxygen concentration in it. And as it rises, the oxygen concentration decreases. So the transfer rate decreases the higher it goes. And the pressure is highest down low as well, because the deeper you are in a water column, you have static head. So you get great oxygen transfer right at the beginning. Actually, shallow basins have some of the best efficiencies from a power standpoint. They just don't have high SOTEs, and we'll talk about the difference there in a minute. And then lastly, you don't have a lot of surfactants that build up on the bubble. This is the alpha factor. We'll discuss that on a later slide. And the important thing here is that oxygen transfer efficiency does not take power into account. This is just the efficiency of transferring the oxygen across that membrane, not the efficiency as far as power or how it hits your pocketbook. And this standard aeration efficiency does take power into account. And this can be used for diffused aeration, this can be used for surface aeration. But the idea is, how many pounds of oxygen can we transfer with the utilization of 1 horsepower over the course of 1 hour? So this is equipment and horsepower and time. And this is essentially the measurement that will hit your pocketbook. This is the important one to take a look at. You could have a device with the highest oxygen transfer rate in the world, but can cost you $1 million a day to do it. It's efficient from a transfer standpoint, but it's not efficient from a money standpoint. So this is the real down and dirty here. So these are numbers that were given to us by an independent lab that's tested tens of thousands of pieces of equipment over the past 30, 40 years. That are no longer in operation, unfortunately, as the proprietor passed away. But the data that they have developed and the standards they've developed will live on. Their findings were that fine bubble membranes are the highest oxygen transfer or efficient piece of equipment in that they transfer 4 to 7 pounds of oxygen per horsepower per hour. We rely on a combination of coarse and fine bubble aeration for what Triplepoint does. For the most part, we do some fine bubble aeration as well, but that falls into the same category range. Coarse bubble, kind of the pure coarse bubble systems, tend to be about 2 to 3 pounds of oxygen per horsepower per hour, and surface aerators tend to transfer 1.5 to 2.25 pounds of oxygen per horsepower per hour. And this kind of goes to show, what I was mentioning earlier is we're smashing together air and water. And in general, it's just less energy intensive to be moving air around than it is to be moving water around. And the coarse bubble application, because it's less efficient, we have to transfer more air. And since we're transferring more air, there tends to be a lower SAE. So you can see kind of the layout of the land here. But the big takeaway here is oxygen transfer efficiency is not equal to standard aeration efficiency. Always pay attention to how much oxygen you're transferring and what that's going to cost you too. Because a lot of people who might not have an efficient approach will tell you, look over here, look how efficient we are, but don't pay attention to what it's going to cost you to put it in. At the end of the day, dollars run everything in the wastewater business. So we know how efficient a piece of equipment is at transferring oxygen and the power that it costs. How do we convert that to real world conditions? And what we want to do here is establish FTE, or field transfer efficiency. And this is where I take a number of corrective factors and we derate that clean water aeration efficiency to make it more fitting with the real world. That clean water testing was done in a lab with control conditions or standard conditions and adjusted to those standard conditions. So we can compare apples to apples, fine bubble to coarse bubble, for example. But it doesn't tell us what's going to happen when we put that device out in a dirty wastewater lagoon system. So we are going to discuss on a later slide the alpha factor. This is kind of the heavy hitter in terms of the field transfer efficiency equation. There is a beta factor, and the beta factor will adjust for the total dissolved solids in your wastewater and relate it back to the clean water test. And TDS is interesting because TDS jointly increases oxygen transfer efficiency, the transfer rate of, if you have more TDS, say you got a lot of chlorides in your water, you get a little bit more aeration because of that. but it simultaneously decreases the saturation point of oxygen, and that we'll talk about that in a minute. But that lowers the oxygen transfer rate, so it's a funky one. There's a correction for temperature. There's a correction for the target dissolved oxygen level, the concentration of oxygen at the elevation, and the temperature that the site features, and the water temperature itself. So there's a lot that goes into this. I would like to say that I could really walk you through this calculation, but this is fundamentals of aeration, kind of a 200 level course, not fundamentals of calculus, and this is not my jam. So I cannot do that math. I leave that to smarter people that are probably in this room. So let's talk about the alpha factor. This is often the most misunderstood and misapplied component of the FTE calculation. And again, this is the factor that takes the clean study and then converts it to what this should look like primarily in dirty, nasty water. And dirty is primarily driven by fats, oils, and greases and other surfactants. What in that water is going to coat the bubble, whether put in by a surface aerator or put in by a diffused aerator, and prevent or make a barrier and prevent that oxygen transfer. Essentially, it just covers it up and prevents the oxygen from crossing the membrane. Fats, oils, and greases do this quite a bit. Soap can do it if you're at an industrial facility, or any other surfactant that changes the surface tension of water. So it's a pretty bulk or heavy-handed factor thrown in there. A lot of times, for example, 0.6 will be used for a municipal plant putting in fine bubble aeration, or 0.65. And that's a total assumption. It's usually okay when done in the municipal space. Most municipal water behaves like other municipal water unless there is a heavy industry on site. Industrially, on the other hand, though, making an assumption like that is kind of a swag. It's a wild, guess, and it's not always necessarily advisable. So if we have a alpha of 0.6, that means we expect about 60% of the oxygen we're putting in to 60% of that clean water test to go actually be transferred in the actual field conditions. This is a place where some manufacturers might manipulate their numbers a little bit and provide higher than normal alphas, and unless the engineer that's doing the design is frequently doing aeration designs, but maybe they haven't done an aeration design in 15 years and they overlook the fact that the alpha that they're being given is not normal, that can severely impact the design such that the end design does not have enough oxygen to meet the demand. So it's important to do some research on your specific water with that type of technology and ask, is this a realistic alpha factor? And if you don't know, or you're an industrial plant and there's only one of you and there's no industry standard knowledge around that, you can actually test this in the field. So this is what we call off-gas testing, where you put a hood over the aeration equipment. And what you can do is you measure the concentration of oxygen at that site. So you know exactly what you're pumping down in there, and then you measure the concentration of the oxygen that's coming off of the off-gas, and you find the difference. And then you can calculate the transfer rate in your water with whatever equipment that's being put in there very, very accurately. So this is a great diagnostic tool to find out, why don't I have enough air, or how much air do I need and I don't want to screw this up. Next, we talk about some dissolved oxygen basics here. So dissolved oxygen is how much we can get into your water is dependent on the saturation point. And this is also affected by temperature. The saturation point is affected by TDS. It's affected by your elevation. But in any given day, at any given site, saturation point of oxygen might be 12. And it's easier to get air. If you were starting from 0, it's easier to get air into a saturation point pond of 12 than it is of 7, for example. So the farther you are away from the saturation point, the easier it is to transfer oxygen to the water. So it transfers all about the delta there. And as you get close, if I have a DO of 10, but I'm trying to get it up to 12, that's going to be much harder than going from 1 to 3. In a wastewater lagoon system, we like to have a residual dissolved oxygen. So essentially, we need the exact amount of air to meet the demand that you have, plus a little bit more to go over. It's kind of a buffer, and it also kind of creates a bit of a oxygen battery out in your lagoon. So you make sure you cover any bumps in the road, or if you get a spike loading of whatever. Usually lagoons are run at around 2 milligrams a liter DO. If you go above that, you tend to be wasting energy to get that air in. And from a measurement standpoint, we get asked this all the time. So how do I measure DO out in my lagoon? Where do I measure it? And you can maybe ask yourself this question, and it's kind of a trick question because there really isn't a right answer. There is no one spot out in this lagoon where I can measure oxygen. If I measure it right here, it's going to be really high. If I measure it over here, it's going to be lower. Maybe back here in this corner, in the middle, it's a little bit higher and in between, but it's not. There is no one point that's representative. If you measure 2 feet down, it'll be different than 10 feet down. So something important to keep in mind. You have to kind of take an average of your lagoon and interpolate a little bit. I'm going to check here on my slide number 24. Okay, good. We are on track. Okay, so from an aeration supply, we're trying to get that field transfer efficiency. We know what our AOR is. We're trying to figure out how we're going to get that air in there. So in my example at 0.2 MGD, we had 250 BOD. You know, how are we going to get it in? So we have a net AOR, as I had mentioned, of 855 pounds of oxygen per day in a lagoon that's 12 feet deep. The air is released at 11.25. We have a standard oxygen transfer rate of 2.1. So across those 11 feet, we are transferring 23.5% of the oxygen that's in the bubble into the water. We're going to derate that though from an alpha factor. This is a municipal plant, we'll say. So an alpha factor of 0.6 is pretty reasonable to assume. Beta factor of 0.95 and theta of 1.024 are pretty standard issue in the aeration space. And we want to target a dissolved oxygen of 2 milligrams a liter. So we want more air out there than the demand, but not too much. Now, when we're pumping that air in, we want to keep in mind the saturation point, because if we're down at sea level, the saturation point might be 10, but up at this site, again, this is fantastical. I'm making it up. We'll say it's 2,000 feet. The saturation at this point is 7.7 milligrams a liter. So it's going to be harder at elevation to get the air into the water. We'll assume it's 30 degrees. When you run these variables through the field transfer efficiency calculation, you come up with an airflow or a field transfer efficiency of 9%. So with the standard numbers, we're throwing in 23 or 24% oxygen. This is what you'd expect in clean water at sea level. But when you take it to the field conditions, you probably apply all the derating factors in dirty water, we're transferring about 9 or 10% of the oxygen to that water. And then from that number, we can find out, well, okay, in order to do that, we need to put in 379 SCFM, or standard cubic feet of air per minute of air, to accomplish the AOR that we want of 855. So let's talk about mixing. That was all oxygen transfer where we're getting air out there, but how are we going to spread it throughout the entire basin? We need to utilize your basin's volume. And mixing is extra important in the lagoon space because lagoons are a very, very large volume and they don't have full floor coverage of aeration. You might have an aerator here, an aerator over there, but you don't have complete mixing at the bottom like you might in an activated sludge plant. So we're putting air in and we've got to spread it throughout that basin. If we're not, then we're underutilizing the volume that we have in our lagoons. So mixing is absolutely critical. And I, beat my chest about this all the time. And I think this is one of the mixing and sludge are the two biggest issues that I see in wastewater lagoon systems. So mixing is really, really critical. So here's just a couple of examples. So here is a video of a cell that was undermixed. It's a sludge holding cell after an oxidation ditch right here. And let's move it forward a little bit because this is not the pace I want. So sludge ended up popping up because it was undermixed, it was under aerated, and the sludge mat actually floated to the surface and ended up breaking the surface aerators that were there because there simply weren't enough of them to get the air out. We ended up doing a pilot with diffused aeration, but we ended up doubling the oxygen being transferred to the water. And you can see here, when we get enough air in, the sludge actually stays mixed in the water column. When it wasn't mixed and it wasn't aerobic enough, it actually floated and it created major odor issues. But you can mix quite a bit of solid. This is about 4 or 5% solids in this basin. And actually, you can look at that over here. That one's not playing ball. So I'll tell you a story about it instead of show it to you. So this is an activated sludge lagoon. We don't see too many of these, but this is one we have over in Michigan. And so they're not just keeping all solids in suspension in the basin, they're actually sending solids back from the clarifiers. So at any given time in this basin, which is completely mixed, there's about 220,000 pounds of solids tumbling around in each one. So if we weren't to do that, those solids would settle out, they get stinky at the bottom, they go anaerobic, and they float to the surface and render the entire facility inoperable. just like this one over here. Mixing is absolutely critical to a lagoon. So mixing is also important from a kinetic rate standpoint. And I had mentioned earlier, the more air we put into a pond, the more we can accomplish in that pond. And this is exactly how. So the principle is, aeration is keeping the bacteria, the waste, and the air in contact. And if we add more air, we can keep more air in contact with more bacteria and more waste and get more treatment. Essentially, we're just kind of supercharging the system. So when you look at a facultative pond, there's no airflow, there's no mixing going on at all. Facultative might look at like something over here, nothing's going on. There's no mixing. So the treatment there tends to be the slowest. When you move up to partial mix, this is what most lagoon systems look like. You can see a partial mix lagoon system here, where you have an aerator here, aerator over there, but there's plenty of dead space in between. Partial mix assumes that lagoon is not perfectly mixed. This is what most lagoon systems look like, with just sporadic aeration here and there. It's a pretty cost-effective way to do things. We'll consider this kind of the normal wastewater treatment kinetic, but we can go above this. The next big jump is actually complete mix, which means every piece of solid that comes into your wastewater lagoon is kept in suspension at all times. So it's always there. Bugs are eating it. There's oxygen all around. We're going to get really, really quick treatment. And the air we're putting in is multiple times more than that partial mix. Partial mix is 2 to 5 standard cubic feet of air per minute per 1,000 cubic feet of volume. Complete mix is around 10 to 15 SCFM per 1,000 cubic feet. So a lot more air, which means a lot more energy, but you can get a lot more treatment. You can treat 4 to 5 times more waste in a complete mix system than you can in a partial mix system. In between, you have a vigorous mix, so you get kind of a lot of concentration, but it's still not, you can tell just color difference. There's not, the color here is not that milky color of that previous facility. It's not as homogenized, but this will treat faster than the partial mix that you see up here. And lastly, you have complete mix, and this is what complete mix might look like if the water's drained. We tend to do this mostly industrially when we need that level of air, but as you can see, the aerators are really close. We got a ton of them out there, and there's no dead space whatsoever because we want every solid that comes out here to be kept in suspension for rapid treatment. So if you have a lagoon system, you're under treating and you can't seem to hit your effluent numbers, you can actually increase the aeration. Usually kind of a step change. You can't just add one surface aerator and expect massive results. But if you increase the aeration, you can get more treatment out of that footprint. Okay. And you can actually see the impact of the mixing in a lagoon system. So the aerator that we install right now, it might be 7 feet across, 7 feet in diameter, and you put it out in a lagoon, you kind of forget about it. But this is before the time of drones. We flew a plane up and took a look at the lagoon system, and you could see, I can maybe zoom in a little bit, you can see the darkened plume of the water here that's being affected by the aerators. This is solids being stirred up, and you're seeing more activity around the aerators than you are in between. This is a perfect representation of partial mix. You've got some great activity here, but right over here, you don't have as much air. And this is a classic view of a partial mix system. But we got out our measurement tools and took a look at the diameter of these areas of influence. And one little 7-foot aerator at the bottom can actually influence treatment as far as 120, or have an area of influence of 125 feet, which we thought was pretty exciting. So, something that's really small can actually be having a pretty big impact out in your lagoon. Depth is a really big factor for mixing too. In addition to oxygen transfer, at least from a diffused aeration standpoint, the deeper you go with diffused aeration, the more mixing you can promote. And this is because mixing is all about the bubble being raised through the water column, and as it rises, it starts to draft water behind it. And as it rises farther, more and more water gets drafted with it to create more of a mixing or circulation effect. So you'll find that diffused aeration systems mix better and better and better the deeper they go. Surface aeration is kind of the inverse of that. Surface aeration is a propeller at the surface trying to force air down into the water. So surface aeration is really, really great at mixing in shallow applications. You got a propeller right there, it's moving a lot of water, and it's creating a great wash behind that propeller from an area of influence standpoint. But if you start getting deeper, some lagoons 10, 12, 20 feet deep, it's harder to pump air down that low when you're starting from the surface of the water. So depth is a real big factor depending on the piece of equipment you're putting out in that lagoon. And in our perspective, it is important to treat the entire water column if you can. If you're not getting air as low as you can, or maybe you don't even have any aeration, maybe you have no aerators and you have a 15-foot deep lagoon, there's no way the oxygen transfer of the surface is getting all the way down to the bottom. And that's an area that's anaerobic, and anaerobic digestion is going to be 15, 17 times slower than aerobic digestion. So adding aeration would be a big plus in those applications. Mixing also minimizes short circuiting. So we're putting air out there, we want to spread it throughout the entire basin. Mixing does that. Mixing also prevents the solid waste that goes into your system from coming out the effluent pipe too quickly. And we identified this in one of the applications that we didn't have any as-builts on a lagoon system and tried to figure out why a lagoon was underperforming before we did our installation. And what we found out is, you can see this green here, we injected some dye over a time lapse, and the green just shoots up in the middle and shoots out over here. And what we identified is right here is where the influent comes in. The influent chamber is actually over here somewhere, and for whatever reason, the influent shoots up about 30 feet away from the effluent pipe. So we identified this lagoon short circuits, and they needed a lot of air if they were going to take whatever dye was thrown up in there and mix it throughout the other basin, so they could utilize this side of their pond. So an aeration system, in that it's mixing, will help you to utilize more of your basin. Something that we're trying to do right now, this is kind of an ongoing real-time effort, is we're trying to utilize computational fluid dynamics, kind of computer modeling, to figure out how do we make our devices better, how do we optimize lagoon system design, where we place our aerators, try to identify why there might be short circuiting, figure out where we want to add baffling. So this is something pretty unique that we've been doing, and what we like about it also is that it actually shows the mixing that I've been kind of blathering on about in a modeled standpoint. So by releasing air right here, just in the center of the static tube, we use this for mixing, we can actually suck water from 14, 15 feet away at the bottom of the basin. The water movement is here and moves up to the surface of the water. So mixing is key, and aeration is a great way to accomplish that. And here's just another CFD of that at the bottom. You can see the streamlines of the water being drafted and flowing upwards, moving outwards, getting into an eddy. And if you look way at the bottom, you can see the water flowing back underneath into the unit. So you get a bit of a spiral roll pattern. And there's more benefits to mixing. Mixing will also keep ice open. A lot of lagoon systems will have ice cover in the winter, which A, prevents oxygen transfer, but B, also traps noxious gases. Most lagoon systems are partial mix. There's some anaerobic activity going on out there. As a byproduct, methane is being formed, H2S is being formed, and as those bubble up, they get trapped. So keeping the ice open is great, and aeration systems will do that for you. They also prevent pond turnover. You might hear operators complain about, in the spring or in the fall, my lagoon turns over, gets really stinky. If you have fish in there, fish might die. That's because the pond levels stratify. Basically, the top of the water might be warmer than the bottom of the water, or vice versa, because of sun or other climate factors. And at some point, conditions will exist, whether it's it's a super windy day or you get a big rain, that flip that tide and cause those two layers to mix. And when they mix, the really oxygen deprived water at the bottom, that might be full of, again, noxious gases like H2S and methane, are mixed with the surface water. And that kind of can kill biology, that can create odors, that's a big deal. If you have aeration out there, you keep it mixed up, and if it's mixed up, it's less likely to have that pond turnover effect. As I briefly mentioned earlier, mixing will dissuade algae growth. You don't see algae in a stream, or you don't see algae in a quick moving river, but you do see algae in a pond that's stagnant. Algae like warm water that's not moving. And the more you get that water moving, the less algae growth you're gonna have. So aeration is really, really key. Another fun one, I'm gonna zoom in on this one too. I love to show this picture. If you look at this, where do you think the influent comes in? Let's take about 5 seconds to think about that. And if you were to guess right here, you'd be correct. And the reason that we can know that is, if you look, there's just a pile of birds right here that are all sitting on the end of this aerator right here. As that influent comes in, it's being stirred up by the aerator, and the birds are chomping on whatever goodies they can find out of that. I just found that pretty interesting. You can see that right there. So what are some additional considerations from an aeration design? These are kind of quick hitters, some things to not forget. Keep these things in mind when you're exploring new aeration technologies. The first one, and I have an entire hour-long webinar on this that I did previously. You can find it on our YouTube channel. But it's essentially trust whoever you're talking to, right? Be a human, but like make sure that they're not blowing smoke somewhere you don't want them blowing smoke. Wastewater, any good wastewater treatment manufacturer is going to have independently tested their equipment. There's a whole American Society of Civil Engineers process for this, where you get an outside independent engineer to test your equipment to the same standards that everyone else is being tested to, and then you can compare them, apples to apples, reasonably fairly. Individuals or companies that don't do this, you don't know what they're getting. What they're designing into your system might be more marketing than it is actual engineering or science. So getting that validation is really, really important. And it's also important from your perspective to make sure that the money you're spending for your town or for your client is actually going to go to something that does what they want it to do. Next, take a look at the manufacturer qualifications that you're dealing with. Unfortunately, in the lagoon space, you can get into some really unsophisticated technologies where you might have had a contractor who's installed a couple of aeration systems, and he's like, "Wait a minute, they're just leaking air out there. That's easy, right?" And anybody who just sat with me for the past 54 minutes realizes that aeration is a bit more complicated than just putting some bubbles in the water. I've seen lagoon systems where somebody went out, some manufacturer went out, bought bed frames, took bubble tubing that you're like soaker hose that you get at Home Depot, and wove it in and out of the bed frame, and then dropped those in the lagoon, which worked wonderfully for all of a couple of days, but ended up breaking pretty quickly. Similarly, this is an aeration system that we actually ended up replacing in 2009. Same kind of deal. They took soaker hose and coiled it up into a pretzel, and it didn't last. It's technology that's not proven over time. It wasn't independently tested. The pond had DO issues, and the aeration system they put in about 10 years prior, they paid all that money for, they had to rip out and start all over again. But yeah, this is just soaker hose tied to cinder blocks. So make sure you're not getting soaker hose tied to cinder blocks. And the whole lagoon aeration market is kind of rife with misinformation. So you have to be judicious and really, make sure you're going through the details on people's aeration calculations, and is their SOTE reasonable? Is their alpha appropriate for this kind of technology in this basin? So you've got to arm yourself a little bit, and you want to beware of outlandish claims. If a manufacturer is coming to you and they only work in wastewater lagoons, and they're saying, "I have the blah, 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 the best thing in the world, no one else can do it this well." The next question would be like, well, why isn't every activated sludge plant in the country using this technology? Why are you only selling to lagoons? Oftentimes, there's some chinks in the armor, and you just got to figure out, what smoke and mirrors are being played. There are a lot of games that can be played, and independent verifications are a really good tool to help kind of get through that. Lastly, it is nice to get a process guarantee from your vendors. Kind of put your money where your mouth is. If you say you can do it, can you do it? Prove it. There's also a couple of other aeration gotchas. So from an aeration standpoint, if you have an air demand, we'll say a lagoon system has 2,000 milligrams a liter of BOD coming in. So it's got a high air demand. So we've got to put in a lot of air to do that. Well, we're not just putting in air, we're putting in mixing too. And when we add mixing, we can get to the point where the air demand creates the mixing that increases the kinetic rate, and then increases the air demand, and it becomes a circular issue where you're putting in more air and you keep having to chase and put in more air to address the demand you're creating with that air. So keep an eye on that. We've gotten into that pickle a couple times. Another thing too is with diffused aeration systems, the more air you put through them, you're thinking, oh, I want to put more air in because I want more oxygen out. Sometimes putting more air in through the same equipment decreases the efficiency of the equipment. So you're putting more air in and you're actually ending up with less air. So keep that in mind. Sometimes if you're adding more air, you do have to add additional equipment to diffuse that air. Elevation is something that is really important to factor in early on in some of our calculations. When we're doing napkin calculations for people, over a conversation, we wouldn't factor in elevation, and that kind of bit us in the butt bit me in the butt a few times, because you have to come back when you actually do the elevation integrated design, and the numbers are very, very different. So if you're doing a calculation in, I don't know, Iowa at 1,000 feet of elevation, but then you go over to Denver and do a calculation at 6,000 feet of elevation, the pressure is different, the DO concentration is different, the saturation point is different, and the amount of air available in the ambient air is lower. The concentration of oxygen is lower. So we're pumping in more air with less air in it. So it does change the efficiency calculations quite a bit. And lastly, there is a big interplay of all the factors that we're discussing. If we increase the flow, we increase the back pressure. Increasing the back pressure lowers the standard aeration efficiency because it lowers the standard oxygen transfer efficiency. If we want to add more, if we put in more air with coarse bubbles, for example, it will actually lower or raise the alpha factor. We put in more fine bubbles, it lowers the alpha factor, which changes the SEFM, blah, 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 blah. So if you change one thing, keep an eye on all the other factors, because oftentimes those will be changing as well. You can't just change one factor in a vacuum. Maintenance is a big consideration as well, and I won't go too far into this, but some questions you should probably be asking is, where are the moving parts? If I have to get out there and fix something, is it out in a lagoon? Is it in a building? Is it in the basin next to, or on the berm next to a pile of snow? How many of these moving parts or how many of these motors do I need to be working on? Are there 10 motors? Are there 2 motors? Are they hard to get to? How often do I have to address the maintenance of the system? Is it every 2 months, every 2 days, every 10 years? How accessible are these if I have to do maintenance, and how easy is it when I get out there? And lastly, what parts are required? Given our timing here, I'm not going to belabor this. I was going to talk about the different technologies, but we won't do that at the moment. Another aeration consideration that's really important, I think, for you guys is modulation. Can I modulate the aeration in my system? Because especially municipally, you're designing for your town, what it might look like in 20 years. You might be growing, but you haven't experienced that growth today. You're going to put all that equipment out there to aerate for, I don't know, 2041 when you don't have those flows and loadings. That means you're wasting money today. So if you have an ability to turn the aeration down in an effective way, you can save power so you don't over aerate. If you have a surface aeration system, you can turn off individual aerators, which will definitely reduce maintenance because you're not utilizing equipment as much, and it will reduce power. It does tend to lose mixing in whatever area those were in. So there is a consequence to that if you're turning off surface aerators. They tend to be on or off. Diffused aeration systems, you can add, excuse me, you can add a variable frequency drive that allows you to take the operating electrical hertz of the frequency of the blower from 60 hertz down to as low as usually around 30 hertz, meaning you can turn the airflow up or down to meet demand. And when you turn the airflow down, the brake horsepower utilization of that blower decreases as well. So if you have a lagoon system designed for 2041, you are spending 30 grand a year on power. If you throw a VFD in there, you can reduce that power usage to maybe $15,000 or $17,000 a year. So $15,000 to $13,000 a year of savings will pay for that VFD in a heartbeat. So highly, highly recommend VFDs. And the other cool thing with diffused aeration, whether coarse or fine, is that when you turn down the air with a VFD, you're still getting aeration throughout the entire basin, throughout all of your diffusers. It's just less air. So you're making sure that you're still getting mixing from the bottom of the lagoon to the top throughout the entire basin. You're not creating dead zones by decreasing the airflow. Another thing I want to hit real quick is circulators. These seem to be really popular in the early 2010s, and they kind of waned off. And the only reason I'm touching upon this in an aeration conversation is because they've generally been associated with aerators. You can see solar circulator right here. This is some of our diffused aeration in a pond, but the solar circulator is right there. It was installed to help keep the pond turned over and to get some, hopefully get some oxygen out there, but it's a circulator. It's a mixer first. It is not an aerator first. And they will argue that, and there's a bunch of companies that do this, that it does increase aeration, and it absolutely does by moving more water across the surface. It's kind of using that surface, kind of that facultative methodology of surface area to transfer oxygen. So you are getting some oxygen, but it's not a very high rate of oxygen transfer because it's facultative. It's essentially the lowest rate of oxygen transfer on that list. So people spent lots of money putting these out there to mix their ponds, and they can mix pretty well, but they might not be getting the aeration performance that they need. Generally, we don't see these being utilized for aeration specifically anymore. It's really just, hey, I don't have power out there, and I need to get some mixing, so let's put a solar circulator out there. I'm going to skip air distribution right now for sake of time, but just, if you want to ask questions later or give me a call, that's great, because air can be sent out via individual airlines and controlled from shore. It can have laterals at the surface of the pond. It can have laterals at the bottom of the pond. There's a lot of different ways of doing this, and there's pros and cons of each. So hit me up later if you want to have that conversation. And this is what I wanted to get to. This is kind of an Aeration 300, not Aeration 200 level content, but I want to get it in front of you because this is something that you can use to change your lagoon today. And this is how you get some free air, some free aeration. So you have a lagoon system here. This is they've drained it to desludge, but we'll say they install some aeration right here. The water comes in. We have BOD treatment, goes to cell 2. We've got BOD treatment. There we go. And moves to cell 3 for nitrification. Usually nitrification happens at a later stage when the BOD is low. So you'll see nitrification happen out here. And in this application, after nitrification, the ammonia becomes nitrite and then nitrate. Nitrate is a molecule right here. It is a nitrogen molecule in the middle with 3 molecules of oxygen bolted onto the outside. There's lots of oxygen in that nitrate. What you can do is add a flow backwards, do a recirculation of 0.25 up to 1 Q or 1 times your flow. And you can use a trash pump or whatever you want. And you pull the water laden with nitrates into this cell. And because the cell is partial mix, or assuming the cell is partial mix, there are some areas of anaerobic treatment. And what happens is these BOD bacteria, these heterotrophs, will actually go to this when they don't have enough air. They will rip off the oxygen molecules, and the nitrogen will just off gas. So essentially, this nitrate brings a lot of value in oxygen into the cell, and these bacteria know how to use it. The other benefit is this cell has low BOD and has a lot of surface area. There's a lot of oxygen that just kind of comes from free wind transfer, but you're not using it because you got low BOD. So when you're pumping this water over, not only does it have high nitrates, it's also got high DO. And you're putting free DO into the cell that can be utilized by your BOD bacteria. Really exciting, something that you should definitely consider if you've got a lagoon system and have access to a trash pump or something. Somebody out there might be thinking, well, I'm just going to double my flow, aren't I? I'm just going to ruin my process. You are kind of doubling your flow because right here, might have been 200,000 gallons a day, and maybe now it's 300,000 gallons a day. But the water you're pumping over is low BOD. So yes, you are increasing flow, but you're also diluting the BOD here. So the net BOD loading on the pond, pretty much the same. There's not really much of a negative consequence. And there's a big boon to recirculation. So we do highly recommend that. As we wind down here, I just want to remind you guys that Triplepoint has a website called Lagoon University, where we put on webinars just like this, and we're able to offer CEUs. And maybe you found us through Lagoon University, but if you didn't, we can offer CEUs, a lot of education, some really, really great content on lagoon specific issues. So check it out at lagoonuniversity.com. And now we're going to move to Q&A. And I'm going to pull up the questions box. We'll see if we have anything. And I will admit that the questions box is the size of a Tic Tac on my laptop here. So I will do my best to read some of these. Okay, a lot of commentary that they lost sound. I appreciate that. All right, I'm back. Oh, yeah, I knew Jerry Shell. Yeah, Jerry Shell was a great guy, Alan. Actually, early on, he gave us a big education on aeration. He's part of the reason why we're here today, actually. Jerry Shell, just for those that Alan mentioned, he's the man who ran GSEE, one of those ASCE independent labs. He was one of the handful of guys that do it. Now there's only Dave Redman, who we work with, and Michael Stenstrom. These are kind of the fathers of the aeration world, in addition to Jerry Shell. All right, I see somebody's looking for some help. We can contact you later. Question was asked, do we need a clarifier after an aerated lagoon? So in general, you don't, unless your lagoon is completely mixed. Completely mixed means all the solids are in suspension, and the complete mixed cells will pass solids to later cells. Everything below that, vigorous mix, partial mix, facultative, solids will settle out because a lagoon is essentially a clarifier in a lot of ways. It's just a big retention time where settleable solids will settle out, become sludge, and break down anaerobically over time. So in general, we don't see polishers or clarifiers after lagoons. What we might see sometimes is a polishing cell. So a 2-cell lagoon might add a 3rd cell at the back end, not aerate it, and just have that be extra settling should they need it. And that's usually used for, if Lagoon 2, for example, turns over, as I mentioned before, and when ponds turn over, they tend to kick up a lot of solids. If Lagoon 2 turns over, that polishing cell will essentially act as a clarifier in the backside. But of all the lagoons I've been to, and it's been hundreds and hundreds, don't think I've seen more than 1 or 2 with a clarifier, and they've been for very specific, sometimes industrial purposes. So Keith, you got a question about the copy of the presentation. So this will be available on lagoonuniversity.com. I know Eve is going to work with it for probably a week or so and make sure it's tidied up in a viewable format, and then it'll be put up on Lagoon University. So just go to that website, you can watch this again. Is installing fixed media in the lagoon going to improve the treatment capacity? Yeah, it will. It's usually important to make sure that the fixed media needs to be aerated as well. Fixed media essentially becomes an attached growth site for bacteria. So bacteria will free float in your water column a lot of ways, especially the BOD ones, but you can grow more if you put stuff in there for them to grow on. You kind of hold them in place. They're like bacteria condominiums. The difficulty with putting fixed media in your lagoon is it's kind of a stagnant environment and it's hard to aerate it super well. And either you get rag buildup on it, which clogs up the media, or they become kind of redworm farms. So you get midge flies that lay red worms, and they eat the bacteria that grows on this. So there could be a kind of a counterintuitive effect there. So we don't see media. Oh, I'm sorry, I'm in the hotel room and I'm being called here. 1 second. Yes?
Did you need to later check out?
Oh. Sorry, I was given a 2 o'clock checkout, and I got a webinar, and it should be done here in a couple of minutes.
Okay,
Yeah.
you're fine.
Thank you very much. Sorry about that. All right. They're being very patient, and I appreciate that. And they gave me a 2 o'clock checkout. So would it be advantageous to aerate the lagoon intermittently? Potentially, if you're trying to do some kind of sequencing reactor where you're trying to get additional phosphorus removal, but in general, what we see is tapered aeration, where you start with a lot of aeration up front, where you have the majority of your demand, and you slowly decrease it thereafter. So I don't think doing it intermittently would be very effective, unless, of course, you're trying to put air on the back end of your system. Maybe you have an effluent requirement of high DO. Maybe you're running your lagoons at 2 or 3 DO, and your permit says you got to come out at 5. Some people will put aeration at the tail end to kind of boost the air at that point. Next questions. Oh, will you discuss tapered aeration? Well, I kind of just did. So essentially, you want to put the air where the demand is. And that's why you always see you usually see tapered aeration designs where the water comes in at 200 milligrams a liter. So that requires a lot more air than maybe the next pond. The next pond might have an influent of 80 milligrams a liter. It just requires less air to meet that demand. So that's why you see a tapered aeration system. How to solve settled sludge in a facultative lagoon. Okay, so I'm just going to stop on that one. Got a lot more questions here. We'll answer the rest of these after the fact with an email. But with settled sludge, you typically add aeration or you remove it. It's either physical removal or you need add aeration or some kind of bacterial treatment. It's kind of a sticky issue depending on how much sludge you have, what the concentration of organics is in that sludge. Is it mostly grit and ash, or is it more like undigested carbon? And you can do some studies to do that. I do believe we have some webinars specifically on sludge. They'll go into much more depth here. But you can also do sludge removal. And in general, lagoons are designed to have sludge removed every 10, 20, 30, 40 years. And most lagoon systems have not been keeping up on that regimen. So starting over, getting rid of that sludge, it can be very costly. But if you start over with an aeration system, you can actually prevent sludge accumulation over time. If that's not an option, you can aerate it, get some oxygen down there. And oxygen can help to break that sludge down, at least whatever part of it is organic. And lastly, if you're using oxygen, you can also use some bacteria as well to kind of boost the treatment in your cell. I don't recommend using bacteria, especially aerobic bacteria supplements, if you're not adding aeration, because you're adding the bacteria, you're creating a demand, but you might not have the supply to meet that. So we will answer the rest of these a little bit later. I appreciate your time and your questions. I appreciate you putting up with my little interruption here. And I look forward to seeing you guys at the next webinar. Thank you very much for your time.